Okay. So, good evening, everyone. My name is Abhinav Arvind, and I'm working as a battery development engineer at Decibels Lab. So, my job is basically to build digital twins, that is MATLAB Simulink models of lithium-ion cells and batteries, and simulate them in different scenarios using test data derived from cell testing machines, and also to develop certain BMS algorithms such as state of charge and state of health estimation algorithms, and test them for system level functionality. So in today's session, we will be going through some of the estimation methods for lithium ion state of health. So basically, we know that state of health is a very important parameter in order to describe how useful a cell will be in its entire lifetime and how long they will last, as in to say how many years, how many cycles, how many kilometers worth of energy can they provide totally. So with that, let's get started with today's session. So we will be like going over through some of the basics of what is state of health, what are some of the possible factors influencing the state of health. And we will also look at some graphical analysis. We will observe like how exactly the capacity fades over time, whether it's due to storage or whether it's due to usage or both. We will have a look into that. And then we will come into like some of the different methods. So we will be looking at some of the simple methods such as least squares, ordinary least square and weighted least squares. Then we'll look into like real-time estimation. So in today's world of electric vehicles, what are all the methods that certain OEMs use for SOC, SOH estimation? And then we'll come to even some of the experimental, that is theoretical methods in which it can be done. So which basically we can't implement in real life. It's just a test bench. So there is things like X-ray diffraction, Raman spectroscopy, STEM, that is scanning electron microscope. Then we go for electrochemical impedance spectroscopy. So these are all like non-destructive structural analysis methods of the cell. So we'll just look into all of this briefly and like have some conclusions at the end. So basically, we will start with some simple definitions here. So what is cell state of health? So if you take any cell, its present condition at this very particular moment describes the state of health, which means that it is a measure of the cell's present condition relative to what it was in a fresh condition. Okay. Obviously, so all cells will obviously always start at 100%. And over time, you will see that there is a gradual deterioration in the ability of the cell to store capacity. So that could be in terms of charge or discharge. So over the time, as and when it keeps getting used, as and when it keeps undergoing multiple charging and discharging cycles, its available capacity will go on decreasing, and therefore its state of health also will go on decreasing. Okay, so usually for like many lithium ion cells, around 75 to around 70% is the end of life. So meaning that once it reaches here, it is no longer fit for primary application. Okay, so primary application, it is no longer fit for this. So they usually go for either they go for secondary applications. There are many companies nowadays that have started up like secondary applications, or they go for basically like recycling. Right. So at certain point, if SOH is 70%, but the cell is not able to sustain a certain amount of current or certain amount of load, then it will be like completely discarded. Okay, so this is in the worst case scenario. So like in like the upcoming 2 or 3 slides, we will understand like what are the different ways in which they can age and what is like the different tests we can perform to understand the aging process. But basically, this is what is the simplest definition of state of health. It is basically the measure of its current capacity to its fresh capacity. Okay, so if you write it in a in a ratio, or if you write it in a certain format, then we can say SOH is equal to present available capacity divided by fresh capacity. This is one way of defining state of health. There are, of course, other ways. They can also talk about in terms of resistance. So basically the internal impedance or the internal resistance of the cell. So we know all the batteries or all the cells have a certain amount of internal resistance. So we can also define SOH as a function of resistance. So we can say internal resistance, so which I am abbreviating as IR present by IR fresh. Okay. So usually the second one is like it's a slightly more tedious process to measure because it involves a lot of testing, much more than what would take to estimate the capacity. So usually many times you will see that SOH is usually represented as a function of capacity. Okay, so these are like two ways in which you can represent state of health. There are like few others where we talk about internal impedance or electrochemical activity, things like that. We will come to that in the later stages, right? But these are the primary ways in which you go for defining the state of health. Okay. So now we know what is state of health. So what are the different factors or what are the different possible situations that cells can face that would influence the state of health, right? So there are actually quite a lot of factors. So in fact, there are 6 major factors, and under this, there are several other classifications, right? So the first and foremost one is temperature. So like your ambient temperature will always influence what is the age of the cell. So, or rather, it will influence how quickly or how slowly it will age. So like it is always essential to maintain a good temperature for the cell. So like you can see already highlighted in green. So the most recommended or the most like nominal way in which you can operate the cell is between 25 to 40 degrees Celsius. So anywhere you are going out of this, suppose you're going to like higher temperatures, say like 55 or 60, you will see that the cell will start to degrade very rapidly. You can see here certain things like irreversible lithium loss, rise in impedance, and then basically there is something called as loss of lithium inventory. So basically you will no longer have the effectiveness of the lithium ion reactions, that is electrochemical reactions occurring within the cell in order to give the required capacity, right? So here you can also see certain electrochemical degradation also starts to occur. So that is your decomposition of the entire cell. So inside there are certain chemical binders, chemical additives, agents that basically keep the cell in one piece. But then if you go on like using at very high temperatures, then this is what can happen, right? So same way, if you go for very low temperatures like 10 degrees or 0 degrees, like sub-zero temperatures like -10. So if you go for these kind of temperatures, then you will see that you will have something called as lithium plating and another very sort of like very dangerous phenomenon called as solid electrolyte interface. So like if you keep operating at very low temperatures, this interface is an interface that will block the reactions from occurring. Okay, so it is sort of like a hindrance to the mechanisms. It will act as a very high resistance. It is basically a layer that builds up on the electrodes and it prevents the effective reactions from occurring. Okay, so this will form lithium plating. Lithium plating is basically dead lithium ions that will stick to the anode. Okay, so they are basically dead, which means they are inert. They will no longer react. They will no longer participate in any reaction. They won't contribute to the cell's behavior or the electrochemical reactions. They will just act as a hindrance or a block. So lithium dead layers can form, it's called lithium plating. And eventually your electrolytes will start to solidify and decompose. So that is another dangerous situation. and that can cause what is called as short circuit, internal short circuit. So to prevent all that, again, it is recommended that all the time the operating temperatures is maintained within this. So of course, even during storage. So if you are keeping it not during operation but during storage, then you can. There are certain guides. There are certain standards which are to be followed in order to prevent excessive aging during storage. So like you can see here, some of the recommended temperatures for storage as well. So you have a good capacity retention even during storage. Okay. So that is with respect to temperature. Of course, like we also know that there is something called as thermal runaway. So if you like operate at like very high temperatures continuously, like 55, 60, then what's going to happen is inside the electrochemical reactions become pretty much unstable, or rather you can say unsustainable, and then they become what is called as leftover gas compounds, and they will eventually cause ignition. So that is thermal ignition, right? So that can like damage the battery pack. So that is the effect of temperature on SOH. So moving to the next one, charge and discharge C rate. So this is just as important as temperature. So we know that if you supply extremely high current during charging, then your batteries can heat up, right? So which is why they restrict the charge rate of the cells usually to something like around 1C or less than 1C. Usually it is something like 0.67C to around 0.71C. So this is to like maintain like nominal operations of the battery, right? But if you continuously charge at 1C or higher than 1C, then it will start to once again tear away at the internal components. Most notably, the one that will start to decompose the first is the electrolyte. Okay, so once you like continuously supply like very high charge currents, then your electrolyte will start to degrade, or basically you can say it starts to form unwanted compounds. Okay, so you can call these compounds as again, these are passive compounds. They don't participate in any reaction, and usually they act again as a chemical barrier, right? So this is the effect of having very high charge rates. So again, here we'll have things like dendrites. Okay, and we'll have something called as like metallic branches. So these are basically like metal compounds that will form due to unreacted lithium, and they will form metallic branches, and this will again like cause thermal runaway. So that is the effect of having high charge C rates. Similarly, you will also see that high discharge C rates will once again wear away at the electrodes, even the electrolyte. So it's always always better to sustain the cell within the recommended charge and discharge C rates. Then we have even the depth of discharge. So like if you are taking, say for example, this is the operating voltage of a cell, right? So if we are starting at say 100%, this is the 100% state of charge, and this is like 0%. The cells will usually last longer if you have the cutoff voltage over here itself. So if suppose this is 2.7 volts, then this will be usually taken care by the BMS itself. So this will be somewhere around 3 or something like 3.1 volts. This is again user dependent, so they can set it as per their requirements. So this cycling the cell between these values will again will cause the cell to last longer, right? So always to maintain a very like a responsible DOD, or you can say like a rather sensible DOD. So never should we like go for 0 to 100, 100 to 0. So this will give very less cycle life. So this is like can give somewhere around like uh, something like 500 to about 800 cycles if you're going for full DOD. But this can give like way more than 1200 cycles to about 1500 cycles if you're keeping the DOD within like say like 85% to about 30 about 25 to 20%. right? So if you stay within this, again, your depth of this, again, your number of cycles, your shelf life will increase. Okay. So this is the effect of depth of discharge on the cycle life, that is to say the state of health. So another important factor would be your storage duration. So the longer you store, the more the cell will start to degrade. So we will see a graph that pertains to this behavior later on in the in this presentation. You will see like how at different at temperatures, how at different storage times, you will see how much degradation can occur. So we will see that in a graphical format. So we will continue the same discussion there. The number of cycles. So this is very important. So more number of cycles, the more the impact on the degradation inside the cell, and then eventually manufacturing variations. So obviously there are like different types of grades of cells. There is A type, there is type B, and then there is type C, which is like one of the lowest quality of cells, very cheaply available. A grade is the one that is used by all OEMs. This is not like it is not publicly available for purchase. Usually they are never available. One good example would be your Panasonic cells, which is used in Tesla or in General Motors, things like that. B grade cells is the one that usually many of the companies would obtain for their testing, for their research and development, validation of algorithms, things like that. So usually like you'll see a lot of B grade cells in India as well, which is brought in from China, and like many companies like Ola, Ather, they all use these B grade cells. A grade cells are like very much for like your global OEMs like your Tesla, Scania, Volvo, Mercedes, Daimler, Chrysler, things like these. So depends on the manufacturing, how good or like how bad is the manufacturing processes that is performed in the very initial stages. So if you have like if you take good care, then you'll have a cell that lasts like up to like 1,500, 2,000 cycles. Otherwise, it will degrade much faster. Okay. So these are like the various factors. Of course, underneath these, there are many other topics that we could discuss, but due to time restrictions, we will not be able to go too far in depth. So now this is the part where we will start having some brief overview on the graphical representation. So on the left side, you can see like just like a very simple way in which you can understand how SOH is like affected. So both in terms of capacity and internal resistance. Okay, so this both of these values are like sort of inverse. So the capacity decreases as and when your internal resistance rises. Okay, so like your internal resistance will rise because over time your electrolyte and your anode and cathode they will like start to become resistive materials rather than conductive material, right? And therefore your storage capacity, that is to say how much lithium ions can be stored, will also go on reducing. Okay, so this is one of the simplest ways you can represent the overall change in SOH. And then as we had discussed earlier, you see that decrease in capacity due to storage, right? So you can see here on the right hand side this particular graph. So you can see how much the capacity loss occurs due to like storage time and also due to temperature, right? So like these two are very important factors, especially when we're talking about electric vehicles. If you're having temperatures higher than 35 degrees Celsius, then you will see that the longer you store, the more and more the capacity degradation occurs, right? So like in extremely hot climates, like in parts of North India or in parts of like Rajasthan, Punjab, where the temperatures are really high, it is like really important to maintain a rather cooler environment so that your battery life is not affected as much, right? So you can see if you have a temperature curve of say 25 degrees or 20 degrees, then you'll have like a very, very minimal loss. This is something like less than 2%, right? So it is always idealistic to achieve this. However, it's not always possible, but the more we regulate the way in which the temperature in the temperature, the more we are able to retain the battery life, right? So this is due to storage, which means that there is no operation during the storage. This is purely in the what is called as open circuit voltage. There is no load connected to the battery. This is how the graphs would look like if it is not under operation. So, but if you want to look at graphs pertaining to capacity loss due to cycling or due to operation, then this is the one to look at. So decrease in capacity due to cyclic usage. Okay. So this is like basically there is not much storage involved here. This is purely due to operation. Okay. So in the next slide or in the next few slides, we will see how exactly this particular graph has been obtained, how what are all the tests that we conduct in order to obtain these graphs. Basically, this is done in a laboratory. So this to understand what does continuous loading and unloading the cell do to the capacity. So if you see here, it starts here, and then you have like almost like 300 to about 400 milliamp hours of loss in capacity, right? So at this point, it has reached its end of life, which means it is no longer suitable for commercial usage. Okay, so we will proceed to the next slide, and here we will see like what are all the different aging tests that you can perform. So it is through these aging tests that we eventually come up with SOH algorithms, which we will be starting in the next few slides. But here you can see like some of the simple aging tests, how you can perform them, some complicated aging tests, which you can see on the bottom of the screen, that is called the WLTP current profile. So this is used mainly in the Europe, Central Europe, in order to analyze how the electric vehicles would perform. So one simple way to test the aging, that is to say the gradual deterioration of the cell, would be to perform what is called as a simple aging test. So this profile is very simple. So all it involves is a certain amount of charging. So this is CCCV charging. So your voltage rises, right? And then we perform a certain rest. So after charging, we'll provide a certain rest period, or you can also call it a settling period. And then after that, we'll perform a discharge. Okay, so this is a discharge. Okay, so this yellow part is the discharge, and the blue part is the charge. Okay, so this profile basically consists of 100 cycles, basically. So 100 times charging and discharging, charging and discharging. And then after the like 100 cycles, we go for what is called as reference performance test. Okay, so we'll abbreviate that as RPT. So RPT is reference performance test. So after every 100 cycles, so it's not necessary that it has to be 100 cycles. Just this is just an example. So it could be 50, it could be 25, it could be 75. It is based on the sensitivity of the tests that we want to conduct. So at the every regular intervals, we perform what is called as a reference performance test, in which we will involve two types of tests. So first one is called as capacity test. The second one is called as pulse test. Okay, so capacity test, basically this is the type of test which is used to see how much capacity has been lost and how much is still remaining. And pulse test is to see how much resistance has changed inside the cell. So starting, of course, at fresh condition and then moving on at every 100 cycles or every whatever intervals is required, we will perform these pulse tests and we will see like how much the resistance has changed. Okay. So this is with respect to the different aging tests. So the same set of reference performance tests can also be performed for this DST. DST stands for dynamic stress test. So basically in this, we have a dynamic current profile. So there is nothing static as such, like compared to the first one. First one was pretty static, but the second one has like a dynamic profile. So you can see here correspondingly what is the voltage response. So as in when the cell goes on aging, you will notice that the voltage response becomes more sluggish. So this will give a clear indication of how much the state of health has changed, or rather how much the available capacity has changed, how much the resistance has risen, things like that. Okay, so here also we perform the same set of reference performance tests. Okay, so again, this will involve like capacity and pulse tests, things like that. Okay, so we can also perform what is called as a drive cycle test. There are many profiles for this. So the one that we are seeing here, this is just one example. So there are like many drive cycles. There is something called as FUDS, Federal Urban Drive Cycle, just pure urban drive cycle, highway drive cycle, HDS, uh, Los Angeles 75, Tokyo. There are many drive cycles that you can perform. So by performing that over a certain amount of time, we'll be able to again understand how much capacity has been lost. Okay. So these are like some of the ways in which like aging tests can be performed. So even in the previous slide where we saw how much capacity has degraded, that was pertaining to the simple aging test. Okay. And currently there is also like tests going on at our laboratory where we are performing aging tests due to dynamic stress test and even the drive cycle. Okay. So these are actually way more elaborate. They take like several months, up to 9 to 10, or maybe in up to like 14, 15 months. So currently they're going on, and eventually we'll come up with more results. So now coming to the major part, that is to see the methods of estimating the state of health. So we will just be briefly going over these methods. Ordinary least square, that comes under the least squares method. So here we'll be talking about ordinary least square. This is nothing but your regression technique. Okay, and weighted ordinary least square, this is nothing but a weighted regression. Okay, so where we will just try to understand through the graphical representation how these two will function. Then we'll come to real-time implementation. So basically, two of the most commonly used ones is Kalman filter based and impedance tracking based. So this impedance tracking is very much particular to like Texas Instruments. So we will just see a basic overview of the algorithm. We will not go in depth into the algorithm itself, but we will talk like just about the basics part of this. Then we'll go into the last part, that is to say the theoretical, right? So theoretical is nothing but lab-based. So purely like where we have a test bench and we purely perform like non-destructive structural analysis of the cells. So that's how experimental works. So starting with the first one, we will look into what is called as least squares approach. Okay. So in order to understand how least squares approach work, we need to take like two parameters from the cell. Okay. So let's not worry about this graph. First, we shall look into the two parameters of the cell. Okay. So one is what is called a state of charge, SOC. Okay. This is the state of charge. Okay. And we have another term which is called as integrated current. Okay. So which I shall abbreviate as IC. Integrated current. Okay. So integrated current and state of charge. These two parameters are what these are what is generally used for utilizing the ordinary least square. Okay. So the reason why we take these parameters is because if we plot them in a graph, if we take the general relationship between these two, it is almost linear. Okay. So if we take the state of charge as the x-axis and the integrated current on the y-axis. So I will write this as IC. And of course, the units for this is amp hours. So please don't get this confused with capacity. This is not capacity. This is integrated current. This is nothing but the integral of time. So if you look at the mathematical form, it is the finite integral of time, current over time. Okay. So if you plot a two-dimensional graph of this, so you will notice that you will have like data that comes something like this. Okay. And if you draw a regression line, you will have a straight line like this. So that's basically what you're seeing in the graph over here as well. Okay. So this can be achieved through a simple method of what is called as ordinary least square. So we know ordinary least square is nothing but your regression equation. Y is equal to A plus BX, right? So like, of course, from here you have to take in B is equal to sum of squared errors, the ratio of sum of squared errors. So sum of squared errors of Y by sum of squared errors of X. Okay, and X and A are your intercepts. So this is going to be your X intercept, and this is going to be your Y intercept. Okay, so these are your this is your simplest way of estimating capacity, right? So if you observe the slope of this particular graph, okay, so yeah, so if you take the slope here, so that is Y by X, you will see that Y by X actually gives you capacity, okay, which I am denoting by Q. So Y over X, if you take the slope of this particular graph, you get what is called as capacity, or you can say this is Q estimate. So this is your estimated capacity. You will never get the truest capacity, as in to say the most real capacity cannot be obtained. You can only obtain a nearest estimate, okay? And usually using ordinary least square, you will have something like 5 to 10% errors. It will be there because of like some of the sum of squared errors, some of which will may not even be accounted for. Uh, that is kind of more into the statistical part. But just for your simplest of informations, this is the like accuracy of this method. By using ordinary least square, we can estimate the capacity. And if you obtain the capacity within, obviously, we can relate this to the state of health, right? So if you have the slope, this is the slope. So if we take the slope from here, we get capacity Q, so which is the estimate, right? And from this, we get the state of health. Okay. So that's basically the entire set of algorithm, the flow chart that you see here on the left-hand side. So whatever I just now described has been also pictorially shown over here. Okay. So if you provide a certain set of test data to it, and I'm just talking on the on the software level. So if you provide a certain set of data, like voltage, reference voltage values, reference current values, and reference time, then if you have a SOC estimator algorithm, and using this estimated SOC and accumulated current, that is nothing but your integrated current, then you will be able to obtain this particular set of data. Okay. So for every 5% intervals of state of charge, you will be able to record uh, the respective integrated current values, and then you will be able to obtain the Q. Okay. So you can see this is the direct formula for ordinary least square. So that is going to be nothing but, so if you take your ordinary least square equation, so your slope is equal to sum of X data into Y data divided by sum of X data whole square. Okay, so if you take this relationship, then you'll be able to obtain the slope, which is nothing but your Q estimate. And that's precisely what is shown here. Okay. This is one way in which ordinary least square can be used. Okay. So there is a more advanced or more appropriate method for estimating this capacity, that is the slope. And that is by using what is called as weighted least square. Okay. So which I have abbreviated here as WOLS, standing for weighted ordinary least square. So it is an extension of ordinary least square. Uh, it is the it has a very similar approach. It is almost the same, except here you will be paying attention to the variation in the data. Okay, so basically you look at data over here, so which is represented by these blue circles. So if you look at this, you will notice that there is a certain spread of data, right? And they are all pretty much random, but there is a certain spread of data. And in weighted ordinary least square, we will choose data that is closest to the regression line. Okay, which means we are giving preference to such data, meaning that they are more accurate in real-time measurement compared to data that is farther away. Okay, so for example, let's take a certain set of data like this, the ones that I'm highlighting here. Okay, so these are your certain measured data, which is pretty much almost along the lines of the regression line, right? So by providing a certain preference to such data, you can have a much more accurate regression line. Okay, so then your capacity Q would change as 1 by sigma, or you can say 1 by, you can say the preference factor, okay, preference factor into the same equation, that is sum of xy by sum of x square. Okay, so this is your, again, Q estimate, which is your estimated capacity from weighted ordinary least square. Okay, so here you are basically providing, or rather you are specifying that you have preference to certain amount of data over other type of data. Okay, so that is your weighted ordinary least square. So these two are some of the simpler, like software level or basic mathematical level ways in which you can estimate the state of health. Okay, so that is using the least squares approach. So ordinary least square and the weighted least square. Okay, so you can see also here, based on the legend, how the effect of using weighted ordinary least square changes. So you can see that your weighted ordinary least square gives a much more truer value of capacity compared to the ordinary least square one. Okay, so there are more advanced methods to least squares approach, things like total least square, recursive least square, which we'll just talk about later part. But I won't be introducing these two methods here because they're mathematically very complex and it simply cannot be covered within the time that we have. So moving to the next type, that is what is called as real-time implementation. So here you can see, like, there are two very important, or rather two very widely used methods. One is what is called as impedance tracking, and the other one what is called as Kalman filter. So of course, I think many are familiar with the Kalman filter, but impedance tracking is one of the simpler ways which can actually give a rather pretty decent or rather accurate estimate of both state of charge and capacity. Okay, it uses a combination of these two methods, Coulomb counting and SOC OCV lookup table, to estimate the true state of charge and capacity. Okay, so basically, like, SOC is obtained through Coulomb counting, which is basically nothing but integral IDT 1 by Q, right? So this Q is here nothing but Q rated. Okay, so this is during loading conditions, which means this is during the operating conditions, which means when the battery is under load. And usually when the no load conditions, or when it's in the like OCV conditions, it uses a lookup table. Okay, so that lookup table will consist of like several sets of data which shows the OCV versus SOC behavior. Okay, so it will have several breakpoints like this. It won't be a set of continuous values, but it will just be a rather breakpoint. So if you have SOC here, you will have OCV here. Okay, so it uses a combination of these two. So it's kind of like a hybrid method, and this will indicate true SOC during non-driving conditions, or basically when the battery is not under operation. Okay, so using these two methods, the maximum capacity of the cell can be computed. Okay, so again, your Q max will then be a function of integrated current, so integral IDT divided by state of charge. Okay, so state of charge, rather this is the change in state of charge. Okay, delta SOC, which means this is like the difference in two SOC values at two different times, right? So even this integral IDT, this is nothing but the change in current, or rather the integral of current over two time intervals, time t1 and time t2. Okay, so if you have this, then again you have your estimate of capacity. This is Q max. Then once again, this is fed into the SOC estimate, that is Coulomb counting. SOC is equal to 1 by Q integral IDT. Okay, so this is basically like a recursive estimate. They'll keep looping these values. Once this is estimated, this again goes back to the Q max equation. Then again, Q max will give you a certain value of capacity. Then again, it goes to the SOC. and so on. It keeps looping over and over. Okay, and that's basically what you see here in the model. Okay, so the model represents the exact same thing. There is also another way, that is by using what is called as a Kalman filter. So uh, like there are many very advanced ways of using Kalman filters. Nowadays very robust Kalman filter methods are available. So some of the most basic ones is your extended Kalman filter. It's pretty simple. You can use a series of algorithms such as update and predict equations, which can basically be implemented in the BMS in a pretty simple way. And it can basically give you the uh, capacity update. So you can see here. So this is what is again a recursive method. So if you have initial values of Q, suppose we provide some initial values, say Qk is equal to 2, or say for example 4. These are just examples. Then it will start to provide a recursive estimate. Okay. So in many in ways in which the state update is performed, same way even the capacity update is performed here. Okay, so you can see a brief way in which how the Kalman filter algorithm works. So in order to maximize the efficiency of the Kalman filter, you can also use uncentered Kalman filters or adaptive extended Kalman filters, even dual purpose Kalman filters, that is called as DKF. Okay, so basically DKF provides a simultaneous parameter and state update at the same time. Okay, so nowadays Kalman filters is like pretty much used in so many ICs of so many BMS. You can actually find many algorithms such as this being implemented. Okay, so Kalman filter and impedance tracking, these two are like very commonly used. This is again the impedance tracking is specific to Texas Instruments. Okay, so if you look at the Texas Instruments inventory, you will see like BQ 27350. This particular IC actually has this implemented already. Okay, so this is very commonly used. Many like small time electric vehicles, especially like two-wheelers, three-wheelers, they use actually this method of tracking SOC and capacity both. Okay. So this is with respect to real-time implementation. There are many more ways actually in which these same things can be modified, used as a hybrid way to get a more sort of easier or more robust way of estimating the capacity and then eventually the SOH. And then there is like also a theoretical or experimental method. Okay. So the experimental method, or we can say the theoretical method, is purely test bench based. Okay, so this is all conducted on a test bench. Okay, so this test bench basically involves like a set of devices or instruments which can provide some complicated, sort of energy rays or things like diffraction rays, reflective rays, penetrating rays, which will give you a 2D map. You can see here a 2D image or a 2D map, which gives you an idea of how the structure inside of the cell looks like. Okay, so this is the non-destructive way of performing. So in which like an X-ray is passed at a certain frequency and at a certain energy through the surface of the sample. So suppose you can see here there are X-rays being passed through the prismatic cell or the pouch cell, and then it is being recorded on a photographic layer. So this layer will then yield certain graphs, which is a function of capacity Q. Okay, so this is a direct interpretation of capacity, and you can also obtain the structural, like structural analysis, or basically the structural overview of the cell, how much the electrode and how much the electrolytes have degraded over time. So specifically, this is after cyclic usage. So this is very useful in understanding what is the cyclic degradation of the cell. Okay, so that is basically one of the ways using X-ray diffraction. And there are certain other similar ways in which Raman spectroscopy is done, laser diffraction is done. There are other methods which is called as STEM, STEM, scanning electron microscope, and transient electron microscope. There are so many other ways in which it can be performed. Even ultrasound can be done, in which you can pass through some sound waves, ultra low frequency sound waves, and then get a structural analysis of the entire cell. So this is one of the non-destructive ways. Another way, which is very, very popular, like it's very widely known today, it's called electrochemical impedance spectroscopy. And basically, this is a AC test where alternating current is passed through the cell, something like 100 milliamps or something like 75 milliamps. So this particular magnitude it's dependent upon the user chosen frequency. User chosen magnitude. So this is a magnitude we choose, and the frequency will be something like 1 kilohertz to about like uh, 5 kilohertz. Okay, so you can actually adjust your frequency of current in this way, so that you can actually obtain a very good insight of how the electrochemical behavior occurs at a microscopic level. So like certain reactions which is not clearly visible at like very high frequencies, like 1 hertz or 10 hertz, these lower frequencies will actually reveal a very good behavior, or a rather very detailed behavior of the electrochemical phenomenon occurring inside, right? So it's kind of like taking an MRI. Yeah. So here you can see like so many results that can be obtained by performing this kind of test. So how and where it has cracked the particles, the cathode, the anode, the degradation of the materials, how much charge transfer is occurring, or how much charge transfer has occurred, the change in internal resistance, the change in diffusion, the change in voltage, the change in concentration of current, the effect of electric and magnetic fields, that is the electromagnetic effects within the cell, how much the structural layers have changed. All of that is possible by performing this test. So once again, this is a non-destructive test in which an AC current is passed through the cell of very low magnitude. Okay, so and this is one way in which you can perform state of health estimation. So this is purely using test benches. Okay, and all the results that have been analyzed through this is purely graphical. Okay, so nothing to do with real life implementation. So this cannot be implemented in BMSs and ICs. It is impossible to do that. So usually they'll go for like graphical analysis here. So you'll come up with something called as a Nyquist plot. So over the frequency, your electrochemical impedance is available. So if you observe your impedance, it will change like this. So over certain frequencies, you will notice your certain set of reactions which contribute to certain phenomenon inside the cell. And this graph basically represents that. Okay. So we will not go too far in depth into this because again, this will require a whole lot of explanation. Even before this, there's a lot of sort of theoretical approach that has to be explained. But here also you can see as a function of frequency, or rather as a function of time, how much resistance is changing and how this can relate into SOH. Okay, so usually in this case, SOH is defined in case of resistance rather than capacity. Okay, so here you can see like the each contributing phenomenon to the internal resistance and eventually the linkage to SOH. Okay, so this is basically the overview of experimental, or basically the theoretical test bench based methods. So there are also like other methods, basically destructive methods in which there is a cell teardown. So again, this is test bench based. This cannot be used in electric vehicles. You can't pull out the cell and keep testing it like this. So this is this is a test bench based. So cell tear down. So you basically cut the cell in half or at a certain cross section, and then you can pull out the electrodes, the active material, the binders, the surface layers, the coatings, the electrolyte. Everything can be done in a controlled environment, in an airtight, watertight area, and then observed using like microscopes to see how much degradation has occurred. So that is one way of doing it. So this is the brief about all of the widely used or very commonly used methods for SOH and basically the condition of the cell. So of course there are many more methods in which SOH and capacity can be obtained. So nowadays, like there is a booming sector in the artificial intelligence and machine learning, in which like certain set of like fuzzy logic controls and neural networking can be combined to give like extremely accurate estimates of capacity and state of health. This is simply like it's too advanced. So even like not many organizations go into this, but nevertheless, it is extremely popular nowadays, even in many other fields. Even in terms of state of charge estimation, many people are looking into machine learning. So where the BMS and the IC, the control unit of the BMS, is very much self-sufficient. So rather than us providing it data, we just train it and then it starts to generate its own algorithm. So that is one way. So these two are combined. So neural networking and AI ML. So apart from this, some more theoretical approaches are there. So in which earlier I had talked about ordinary least square and weighted ordinary least square. So there are more advanced versions of this. It is called total least square, so abbreviated as TLS. So total least square and also what is called as ATLS, adaptive total least square. So here the variances along the x and y axis and the weightage function of x and y axis, all of that has to be considered. And this is like way more complex because here you have to consider something called as Gaussian distribution. So Gaussian distribution of data. So it's a necessity in order for these two methods to be performed together, without which these methods will fail. So the complexity of these two methods is so high that it can only be performed on a system level. That is to say, on a computer or on a lab-based device. So it cannot be implemented that easily in life because there are so many mathematical issues that come up when it comes to like code generation and compilation, deployment into the hardware, targeting, things like that. Okay, so but nonetheless, total least square and adaptive weighted least squares, these two are like one of the more accurate sort of mathematical approaches, and they certainly give way more accurate results than the ordinary least square ones. So I had also talked about advanced Kalman filters. So apart from EKF, you also have dual Kalman filter, sigma point Kalman filter. Uh, these are all like much more advanced and can give a much better, and more accurate estimates of Q. So algorithm is like a bit more complex. So showing it here may not exactly be possible. So you can look into some references pertaining to these two methods. So SPKF, especially SPKF, in fact, it is like pretty popular nowadays when it comes to Kalman filter methods. So another method, which is like used in real time, it is called recursive least square. So this is actually, it has been successfully implemented, and recursive least squares is one of the more easier methods of estimating capacity and state of charge, state of health, all of this. So basically, it's like a slightly more advanced version of OLS, but not as mathematically complicated as adaptive weighted least square or total least square. So of course, there are other hybrid methods also, which is currently being experimented. So you have recursive methods, which is like combined between Kalman filter and recursive least squares. You have statistical approaches. Okay, so like basically using statistical data, like probability distribution functions, things like that, along with Kalman filter. And you also have what is called as equivalent circuit model. So this is test bench based again, so it cannot exactly be implemented directly because it is very difficult to perform code generation on a certain cell model. It's not that directly implementable, along with recursive least square. So these are like some of the more hybrid methods in which it is performed. Most of the complexity actually comes because of the fact that you don't have data directly available. Rather, you have to take derivatives of certain data. Okay. So to summarize, there are quite a lot of methods that exist for SOH estimation. So we have seen in this webinar, to summarize, we have seen least squares approach, which is very much mathematical. So here we had talked about regression lines and curve fitting, things like that. And we had also talked about something called as a priority factor. That is for the weighted least square. So you're providing priority to certain data over other data, or you can also call this preference factor. Okay. So another term for this is what is called as variance, which is denoted by sigma. So if you're aware of standard deviation and variance, This is basically where it's calculated from. So there is actually a lot of stochastic and statistical methods involved in the least squares part. So we had also talked about some real-time applications. So in real time, we had seen Kalman filter and we had seen impedance tracking. So actually, you can see that impedance tracking is very widely used. So this is one of the simplest and very, very easily attainable sort of algorithms because its complexity is very low. It does not require excessive amount of mathematics or complexity like how other methods use. So this is just a simple variation of the Coulomb counting method, right? So all you have to do is provide some SOC, OCB lookup table data and provide some starting data for the Coulomb counter, and then pretty much it will provide some recursive estimates on its own. So these are some of the ways the methods we had talked about, of which all of these, only few of them are implemented in the real life. So you cannot implement each and everything, right? That is because of something called as robustness. So we have to consider what is called as robustness of the IC. In real-time applications, you can't dump huge megabytes or gigabytes worth of algorithms. It may be fine on the laptop or computer, but it will definitely not work on the IC, right? So the RAM cannot sustain such heavy amount of data transfer and it'll crash. So considering the robustness is extremely important, which is why you can see that very, very large algorithms cannot be implemented in the IC. So notably, these are all the methods which is not easy to implement. So they are too complex. Okay, rather, instead of going for real-time estimation, we go for something called as online estimation. Okay, so basically, online estimation is a method in which data is transferred, or you can say data is logged. Okay, using certain communication protocol, CAN, UART communication channels can actually log this data and send it to a server. So once it is sent to a server, it is then sent for estimating using certain algorithms, either Kalman filter, or you can say like least squares, dual purpose Kalman filter, things like that. So data is logged and then it is sent to the server. Okay, so either this can be done. This is called as online estimation. This is a little bit more challenging. Usually people try to avoid this and they go for easier, simpler methods like least squares, very, very simple, basic least squares, Coulomb counting, lookup table based, or Kalman filter based, which can be easily implemented into the BMS and work as offline estimation, which means this can be directly implemented into the BMS itself. Okay. So yeah, these are the conclusions that we can draw up from all of these existing methods. So with that, we come to the end of this session. We can now have a short, about 10 minutes maybe, worth of Q&A. So